Here we have a Rosemount Model 1151 differential pressure transmitter. It is being powered up by a 24-volt variable supply. We are measuring the loop current using a Fluke Model 87-5 multimeter, reading about 12 milliamps right now. The present calibrated range on the transmitter is 0 to 1,000 inches of water, and we're applying about 500 inches of water air pressure using this pump. So I pressured it up to about half scale, 50%, 12 milliamps. And what we're doing here, in addition to looking at the current, we're also monitoring what the transmitter is seeing through this HART communicator. This is an Emerson Model 375 field communicator for HART and for field bus. We have it configured for HART operation right now, and you can see on the screen we're looking at the current process variable of 500 inches of water, the analog output of 12 milliamps, lower range of 0 inches of water, and upper range of 1,000 inches of water. So what I'd like to do here is explore in brief how this HART communicator works. HART stands for Highway Addressable Remote Transmitter, and it's a digital protocol that was invented to work in superposition with the normal 4 to 20 milliamp DC loop. So the DC 4 to 20 milliamp loop that everyone is familiar with analog transmitters really doesn't change, but we've added to it the capability of superimposing AC voltage and current signals on those same two wires. The transmitter itself is now smart, and it has a microprocessor built inside that knows how to interpret and how to send those digital signals. So using this technology, we can interrogate the transmitter using a computer. We can take a look at its range values, we can change the range values, change parameters such as damping and linearization, perform calibrations, assign tag numbers, all kinds of stuff we could never do in the analog world. Likewise, we can read information from the transmitter that we were never able to do either. Things like self-diagnostic information, error tags, even in some cases ambient temperature. So it's a fantastic expansion of capability using the same old 4 to 20 milliamp DC loop technology we've had in use in industry for decades. And indeed, HART itself is not exactly a new technology. It's a 1980s era technology, but it's still in very wide use. What I'd like to do first is show what the HART communication signals actually look like using a meter. An oscilloscope would be an ideal tool for this, but for right now I'll demonstrate how to use a normal Fluke meter to do the measurements. This is another Fluke Model 87-5 meter. These Fluke meters do a great job of distinguishing between AC and DC signals. So I'm going to set it on AC, and when I attach the meter leads to the two terminals on the transmitter, we're going to notice about 100 millivolts worth of AC communication. That signal you see right there, the 100 millivolts or so of AC voltage, is what is constituting the digital signals between the field communicator and the transmitter, talking back and forth. Those pulses of voltage, binary ones and zeros, communicating digital information. Now if I stop this process, if I turn the communicator off, notice what happens to our AC millivoltage. It goes down to practically nothing. We're looking at the quiescent noise voltage here. If I restart the HART application, on the other hand, we'll start to see that voltage pick up as the communicator begins to establish communications with the transmitter. And here I want to go online. There we are. We're looking at our device setup screen, process variables. Whoops. Back to our home screen. There, the online screen, the process variable, analog output, and range points. And once again, we see the AC millivoltage bouncing around as the data goes back and forth. A very, very important element to have in the circuit in order to enable the HART communication is a resistance. Now typically this is a 250 ohm resistor. It does not have to be exactly 250 ohms for the HART communication to work, but the loop must have some resistance in it in order for HART to function. If it does not, the HART communications will cease. I'll demonstrate this here. I'm going to take this 250 ohm resistor and bypass it. Notice my DC current is still 12 milliamps. I still have 24 volts supplied from the power supply. The pressure transmitter still has about 500 inches of water column pressure, and my current is unchanged. So as we've seen before, the presence or absence of a resistance in the DC circuit really doesn't affect the basic 4 to 20 milliamp analog signal at all. However, back here at the communicator, we see the error message, device disconnected. If I retry, what we're going to see is the same error message again. It cannot talk to the transmitter. If we take a look at the voltage signal here with our fluke meter, while we retry communication, we'll see exactly why it can't talk. We're reading just a couple of millivolts noise voltage. I'll hit the retry button, monitor this meter, and we see nothing. I'll retry again as we monitor the meter, and we see nothing whatsoever. Here's what's happening. The filter capacitors in this DC power supply effectively form a low-pass filter. What they are doing is they are drowning out, or they are squelching any AC voltages we try to impose in these same two wires. Recall that the HART data signals are exactly that, AC voltages. So, with the filter capacitors here on the power supply being effectively in parallel now directly with the transmitter, it squelches any attempt to communicate in digital form. That's why we have to have a loop resistance here. Without the loop resistance, that DC power supply with its filter capacitors become directly in parallel with that transmitter. With the resistor in place, however, we have some impedance standing between the AC HART signals and the filtering effect of the DC power supply. That is why a loop resistor is necessary for HART communication to take place. So now, as I look at my AC millivoltage across the transmitter terminals, and I press the retry button, now we see the voltage reappear, and it's communicating once more. That's a very easy detail to overlook, very easy to miss if you're setting up a transmitter on a test bench to do a HART communication activity with it. You need to ensure you have a loop resistance. And this loop resistance, again, does not have to be exactly 250 ohms. It can be anywhere from around 250 ohms up to about 1,000 ohms. That's what Rosemount specifies. But some resistance does have to be in place in order that the DC power supply does not squelch the AC signals that the communicator and the transmitter are trying to generate.